I have our syllabus calendar up. I don't have test 2 graded yet. Definitely for Friday. So we're going to start on packet 3 today. The packet I just handed out is for the rest of the semester. So it has up through test 3 plus 5 or 6 more classes that go up to the final. The final, yep. Your next quiz is in a couple of weeks.
There are only 3 tests before.
3 tests plus a final. Yeah. And then I also handed out your third project, which is on data, doing linear regression, which you've probably done in a previous class, but we're going to use calculus to figure out how your calculator or computer comes up with that line of best fit. So that's the third project, and it's not due, it's due on the 23rd. Okay, so the first couple pages of your packet, the first page is a in-class quiz that we're going to have on class 32. It's on the first page so that when we get there, you can just rip it off to hand it in. The next page is guidelines for related rates. So that's something that's like a note sheet you can bring to your test. And then we get to today, class 26. All right, so today we're going to learn the technique of implicit differentiation. We use it when the equation for a curve is not written in the typical way that we see it, y equals stuff with x's format.
That's when like y is to a power, right?
Yeah, y could be to a power or lots of other things, but yeah. Okay, so let's do an example. I want to find an equation for the tangent line to this curve, right? So I've got a picture of it here. That is its formula. It's kind of a crazy complicated formula. Solving that formula for y would be really difficult, right? I'd have to square the x squared plus y squared, distribute my x plus 2. Solving it for y would be some really messy algebra. So I'm not going to do that. Instead, I'm going to use a technique called implicit differentiation. So first, let's draw a picture of what we're looking for. I want to find the equation of the tangent line to this curve at the point -1, 1. So there's the point -1, 1. If I draw a tangent line here, not the best tangent line I've ever drawn, but you get the idea. I want to find the equation of that line. What's the equation of a line generally look like? mx plus b, yep. So b is my y-intercept, right? It looks like it's negative something, right, according to my picture, but that's about all I can get just by drawing it. And how do I find m? The derivative, right? The slope of a tangent line is the derivative. So I need the derivative, and then to figure out what b is precisely, I need to know a point on the line, and I can use this point because the point of tangency is on the curve and on the line. Right, so this point right here is the point -1, 1. So I have a point on the line, and I just need the slope of the line, and I can find the equation of the line. Okay, so let's work on the slope part. The slope of the line is dy dx, evaluated at the point -1, 1. The slope of the tangent line is the derivative of the function, dy dx, at that point, at the point of tangency. So I need to find dy dx. So what I do is I'm going to start with my really messy equation. And I'm going to take d dx of both sides. So we did a similar technique when we were trying to figure out the formulas for inverse functions, like the log function and the inverse trig functions. We started with an equation we know was true. We know this is true because it was given to us. And we take d dx of both sides. And then I'm going to have to introduce a dy dx in here somewhere, and then I'll solve for it. Okay. So as I work on taking the derivative of the left-hand side, it's going to be messy. There's a lot of rules going on here because I've got a product right here. And I also have a power, some stuff to a power. So I've got a chain rule within the product rule. Derivative of the right-hand side is easy. So we'll save that for last. Okay. So I'm going to start working on this piece. I want to take the derivative of that. Okay. This other piece is just separated by subtraction, so I can just take its derivative separately. Okay, so when I'm working on taking d dx of this product, I got to start with the product rule. Okay, so I'm going to have first times the derivative of the second. Okay. This is some stuff to a power. How do I take its derivative? Yep, I bring the 2 down, copy the stuff, reduce the power by 1, but then I still have to multiply by the derivative of the stuff. So I need to figure out what is the derivative of x squared plus y squared. Well, what's the derivative of x squared? 2x. What's the derivative of y squared? You're super close. Yeah. So I'm taking d dx, right? D dx, which means I'm taking the derivative where x is my variable, right? So when I try to take the derivative of y squared, it's not just 2y, because y is not the variable I'm interested in, right? It's x. Yeah. So y, though, is actually a function of x. Y depends on x, because I could solve this equation. You know, one way to approach this problem would have been to solve for y in terms of x, and then done the derivative that way. So y is actually a function of x, so I actually have to do the chain rule here, right? Imagine, instead of that saying y squared, that says f of x squared, right? Because y is a function of x. So it's actually a chain rule. You bring the 2 down, you copy the stuff, but then you still have to multiply by the derivative of the stuff. So it's a lot easier to picture sometimes if you imagine it as an f of x. So if I wanted to take d dx of y squared, that's the same thing as trying to take d dx of f of x squared, because f of x is just a fancy way of saying y, right? So if I wanted to do that derivative, now that's just some stuff squared, right? So you bring the 2 down, you copy your f of x, you multiply by the derivative of the stuff. But I used y, so this is actually 2y. And then instead of f prime, I used dy dx. That kind of makes sense? Why you need to throw that dy dx in there?
Well, it's the derivative of y. Y is up there.
Yeah. Yeah, and then once I finish taking the derivatives, I'm going to solve for dy dx. Yeah. All right, so back to my derivative. Not done yet. That was the first half of the product rule. That was the first times the derivative of the second plus the second, x squared plus y squared squared, times the derivative of the first. What's the derivative of x plus 2? 1. Minus the derivative of 9x squared is 18x equals d dx of -4 is 0.
Wait, why is the -9 just -18x?
It is. -9x squared became -18x right here.
Okay. So where the second x? Y squared?
The second half of the product rule.
Oh, right. Okay.
Yep. Yeah, so maybe I should write it down. This was first. This is
Right, of course.
Derivative of second. This is second. This is derivative of the first. So that stuff underlined in purple is the product rule.
Right.
And then you have the minus 18x for the second term there. Okay, so now I have a dy dx in my problem, right, in my equation. And that's what I want to know. I want to know dy dx at a specific point, right? I want to know dy dx when x is -1 and y is 1. So if I were going to solve this equation the way it's written for dy dx, that'd be a lot of messy algebra, right? I'd have to get that dy dx by itself. It would take a lot of work. But because I'm only interested in the derivative at one particular place, -1, 1, I could plug the point in now before I start trying to do any manipulation. And then I'm just going to have an equation with numbers in it and one unknown, dy dx. So everywhere you see an x, we're going to replace it with a -1, replace all the y's with 1s, and solve for dy dx. Yeah, you have to know both coordinates at the point. I can't just tell you x. Yep. Okay, so replace x with -1, -1 plus 2 times 2. X squared is -1 squared, y squared, 1 squared. I'm not going to bother writing to the first. 2 times -1 plus 2 times 1 times, I'm just going to write y prime, save me a little vertical space. X squared, -1 squared plus y squared, 1 squared, squared, minus 18 times -1 equals 0. So I replaced every x and y with a value. X is -1, y is 1. And now the only unknown in that whole equation is y prime. So it's just a bunch of numbers and a y prime. I should be able to solve this. So let's see, I'll just simplify a little bit at a time, see if I can solve for y prime. So -1 plus 2 is 1. So this is 1 times 2 times -1 squared is 1, 1 squared is 1, so 1 plus 1 is 2. So that's -2 plus 2y. Y prime, yes, thank you. And then this is going to be 2 squared, which is 4, plus 18 equals 0. Of course, I'm out of room. All right, so simplify a little bit more. 1 times 2 times 2 is 4. -2 plus 2y prime plus 22 equals 0. Now what? Distribute the 4, yeah, so I get -8 plus 8y prime plus 22 is 0. Combine my like terms here, so I'd have 8y prime plus 22 minus 8, 14. Okay. You guys know how to solve this from here. So subtract 14 from both sides, divide both sides by 8, so you get -14 over 8, or reduce that, you get -7/4. Am I done? Is that the answer? No, why not? That's just the slope. I asked you to find the equation of the tangent line, right? That's the slope of the tangent line. So I'm almost done. Right? I now know that my equation of the tangent line looks like y equals -7/4 x plus b. And I just have to figure out what b is. And for that, I need a point on the line. And I was going to use -1, 1. Sure. That -2? I think I just multiplied those two together to make -2. 2 times -1. I don't remember. Let's see. Nope, that was just an x. Yeah. Got it? Okay. All right, so now I just have to solve for b. So I get 1 equals 7/4 plus b. Subtract 7/4 from both sides. So b is 4/4 minus 7/4 is -3/4. So my final equation is going to be y equals -7/4 x minus 3/4. And that agrees with my rough sketch. It looks like it was negative, not quite -1 for my y-intercept. It does look like it has negative slope if you go back and look at the picture. The tangent line I drew, it looks like it has a negative slope. Y-intercept is negative, somewhere between 0 and 1. So that agrees with my rough sketch. If I want to be really sure, I could graph both my figure and my tangent line using GeoGebra. So let's do that quickly and just verify that we did this all right. -7/4 x minus 3/4. Yeah. Okay. X plus 2 times x squared plus y squared squared minus 9x squared equals -4. So GeoGebra can graph implicit functions, which is a big plus on GeoGebra. Your TI can't do it unless you solve for y, which is a pain in the butt, sometimes impossible. Okay, so there's my curve that you were given. And I'm going to graph the line that we just found. Y equals -7/4 x minus 3/4. And -1, that looks a little funny. Yeah, it doesn't look like it's hitting my tangent point. Did I make a mistake? -7/4 is -1.75 minus 0.75. Yeah. Did I type in my? Oh, it expanded it all.
Bubble's supposed to be there?
Yeah. 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 No, that's a little bubble.
So where's precision? Marking 0.
Oh, yeah. Yeah, it's part of the graph. Yeah, it doesn't look like it's tangent at -1, 1. We must have made a mistake somewhere. Darn. I shouldn't have checked it. Well, you get the idea, right? I'll find the mistake while you're working on your activities. I know, I'll find it. So if you have an equation that, just to summarize, if you have an equation that you cannot solve explicitly for y, we say that equation defines y implicitly, and the technique we just used is called implicit differentiation, where you take d dx of both sides. You end up having to use the chain rule, and that introduces dy dx into your equation, and then you solve for it. Okay, so how do we know that we need this technique? The equation has x's and y's all jumbled together. Okay, if you can't have it like y equals a bunch of stuff with x's, that's when you use implicit differentiation. And the thing to remember is that whenever you're taking the derivative of a term that has a y in it, you have to multiply by the derivative dy dx because of the chain rule. Solving for y there would be really... Yeah. All right. Yeah, I guess you could. Yeah.
The reason for implicit differentiation.
But every time you take a... Yeah. And sometimes the algebra is actually impossible. Like you actually can't get y by itself. In this one you can. Both of the times you said you'd have to take a square root, you have to write plus or minus. So then you're going to have 2 plus or minus square roots in that final equation. So it's just going to be super ugly. Yeah. So that's actually turns into like 4 different equations that you have to take the derivative of. Yeah. All right. So I'm going to have you start on your activities, and I'm going to find our mistake.